Now that we saw that the continuous, that the space of functions, continuous functions that are vanishing at infinity forms a Banach space, being the closure of the compactly supported continuous functions, we want to study the dual of this Banach space. This result goes as a theorem due to Ritz, because it's very connected to the Ritz representation that we already saw. So it's called the Ritz duality theorem. Okay, and the statement is the following. So suppose we have a boundedly compact metric space. Then the continuously, so you take the continuous functions that are 0 at infinity on E, and we take the dual, then this space is isomorphic as a Banach space to the Banach space, which we previously called MEPE, namely the real measures, the space of, is the space of real valued measures on E, with on the sigma algebra of the Borel sets of E. This is equipped with the total variation. Okay, and actually we can express explicitly what is this isomorphism. So this is via the map that to every such measure associate the functional that to any continuous vanishing at infinity function on E associate the integral of f in d mu. Okay. Now let me stress that. So this statement is really saying that this map is a linear isometry. Okay. The result states that this map is a linear isometry. And we should actually clarify that really this map is well defined, that this defines an element in the dual, and then more difficult part will be to prove that every element in the dual can be expressed in this form. Now, in other words, we need to prove the surjectivity of this map. Okay, let's start. Okay, so let's first prove that the map is well defined. So let's take one such measure, and then we set the functional associated to mu to be the one by definition gives the integration with respect to the mu. This is for all f continuous vanishing at infinity. Okay, let's clarify that this is really a function. Okay, so let's notice that, so this number, okay, which a priori we don't really know if this is finite, but we are going to prove it now. So remember, mu is a real value, so it can be written as a positive measure minus another positive measure. So with mu plus, mu minus positive measures. So we know that the total variation measure can be written as mu plus plus mu minus. Okay, so this by definition is the integration of f respect to the mu plus minus the integration of f respect to mu minus. Okay, this is by triangle inequality, by property of the norm. We can write it as the integral of the absolute value of f in the mu plus the integral absolute value of f in the mu minus. Okay, so so as we said, that because of this property here, then we can, this is equal to the integral of f respect to the mu, the total variation. Now f is a continuous function that outside a compact set is less than epsilon. So in particular has the sup is bounded. So this is, we are seeing this function as a subset of L infinity. So this is less or equal than the sup norm of f times the measure of the whole space. And this is what by definition is the total variation of the measure. So in particular, these two numbers are finite, so therefore this is finite. And so this is okay, so well-defined number. Moreover, we saw that this norm is bounded linearly by the norm of mu. And therefore, what we conclude that this operator is, okay, first of all, it's well-defined, and it's continuous on C00. Okay. Moreover, it's clear that this operator is linear because the integration is linear. And therefore, we have that this operator is indeed an element of the dual. And we also proved that the operator norm is bounded by the total variation of mu. And this is this calculation here. Okay, good. So in other words, this is a Lipschitz embedding, a Lipschitz immersion, a Lipschitz map. We don't know that it's injective yet. Now we have to prove the other inequality and to prove this anisometric embedding. Okay, so let me put it as a claim. So mu goes to lambda mu is an isometric embedding. In other words, we only need to prove the other inequality. Now, recall that for real valued measure, we have a decomposition that we know that there is a set such that mu plus can be seen as mu restricted to B, and mu minus is mu restricted to the complement of B. As I said, there is we can decompose a space on which the measure is positive and another one on which and the complement is on which mu is negative. Okay, now I'm going to do a calculation, but first of all I want to warn you about something. So I will take now the characteristic of B minus the characteristic of BC, and it seems that I'm going to calculate the operator because I'm going to integrate this with respect to mu. But pay attention that one cannot calculate this the operator on this function because this is not a continuous function unless one of the two sets is trivial. Okay, so this is not, but I'm going to still calculate the integral. But we consider its integral. Okay. So the integral of characteristic of B minus characteristic of B complement with respect to the mu, this is, of course, is the measure of B plus the measure of B complement, minus the measure of B complement, and this is the same as saying B mu on B plus mu of B complement, which is equal to mu of E, which is the total variation. So now, see, if this function were in C00, which is not, then we would prove that the operator admits in a vector this is our norm 1, and the value is exactly the total variation of mu. So now, as I said, this is not in the set, so we have to approximate. No? So what we do, we should approximate using horizon lemma. Okay, let's approximate. Remember that the total variation measure is a Borel measure on a abundantly compact space. This is going to be regular. And therefore, for all epsilon, we can find a compact set inside B such that the measure of this compact set is almost the measure of B, and K minus inside the complement of B compact, on which the measure of K minus is almost the measure of B complement minus epsilon. Okay. By horizon lemma, there exists a function continuous with compact support such that the supernorm is less or equal than 1, then f restricted to the complement, so it's not okay, to k plus is constantly equal to 1, and f restricted to k minus is constantly equal to -1. So what I'm saying is the following. Suppose you have this set B. This B is this set. So now horizon tells you that you can put a compact set inside K plus, so the regularity tells you that you can put a compact set inside B, which is almost the same measure, and another compact set outside of B, that's almost the same measure of B complement. Now horizon tells you that you can define a map that is 1 here, it decreases, and then it's going to be 0 outside. But then we will add it, or we will subtract a function that is 1 on K minus, and then it's going to vanish and going to be 0 somewhere else, as outside a neighborhood of K minus, which will not touch K plus, and therefore we are going to have a map that is going to be 1 on K plus, -1 on K minus, and is between -1 and 1, and has compact support. So outside a compact set, then the function is 0. This is what we have. Okay, so now we are ready for the calculation. What we have is, okay, now for this function here, we calculate the operator mu. So, which by definition, this was the integration between f and the mu. And now we split this integral as the integral on K plus the integral on k minus, and the integral on what's left, e minus k plus union k minus of f. Now, on k plus, the function is 1. On k minus, the function is minus 1. And what's happening about the rest? Okay, let's leave it for a moment like this. Now we are going to bound. So, okay, the first one is actually the measure of k plus minus the measure of k minus. Now we're going to bound as with the sup norm of f infinity minus, because we are bounded from below, sup norm of f infinity times the absolute value, total variation measure of e minus k plus union k minus. Okay, so now the way we choose k plus and k minus, the measure was almost equal to b. The second was almost equal to b complement. Now the norm of f is 1, and now what the absolute value of total variation is a measure, right? So I can write this as total variation of I split E as B plus and B minus. This is B minus measure of K plus mu of B complement minus the measure of K minus. Now each of them is less than epsilon. So what we have in total, we have that this is greater or equal than the measure of E, because putting together B and B plus is sorry, this was a minus. So now this is a total variation of E minus 4 epsilon. So epsilon was arbitrary, and therefore gives that the norm of this operator is equal to the total variation of mu. So we proved that the map we are considering to mu associate this operator is an isometric embedding. So the map that to every mu associate lambda mu, so this is an element in C00 star, is an isometric embedding. Actually, what we proved it is norm preserving. Is norm preserving. So preserving the norm. Now we need to prove that it's also linear. So need to explain that it is linear. Okay, let's see that it's linear. Okay, linear in mu, right? So what we are asking is lambda of mu plus nu, is it equal to lambda mu plus lambda nu? Okay, so what we do, so state mu and nu measures, real valued measures. So now what we do, mu has a decomposition, mu plus minus mu minus. Nu has its own decomposition, mu plus minus nu minus. with the property that all of these are positive measures. But then what we have is that mu plus nu as a measure, we can decompose it as mu plus plus mu minus minus mu minus plus nu minus, and so each of these are also positive measures. So we find, so what do we have? We have that how you define the operator on for the sum. So lambda mu plus nu of f, this is the integral of f in the mu plus nu, which by definition of for real valued measures, this is the integral respect to the positive part, positive part, minus the integral with respect to the negative part of the measure. But as we said, this is by linearity of the measures, this is just mu plus of f plus lambda nu of f. So we prove that this map that to any mu associate lambda mu, it's a linear map that is preserving the norm. So it's an isometric bending. What's left to prove is the most important part, that this map is surjective into the space of dual elements of C00. Let's summarize where we are. So for every real measure mu on E, we associate an operator mu, a lambda of mu, and that is a linear, continuous linear map on the space of continuous functions vanishing at infinity. And we prove that this is a linear map that is norm preserving. Okay, so what we are left to prove for identifying this dual with this space is the surjectivity of this map. So now we prove the more important part. The more important part of the proof is left, and it is surjectivity of this map. Okay, so let's take an element of the dual, and we want to express it as lambda mu for some measure mu. Okay. We are going to rely on a theorem due to Ritz. So this theorem we are proving, we are calling the Ritz duality, but we also prove the Ritz representation theorem that represents every positive linear operator on compactly supported functions as given by the integration of a measure. So we shall use Ritz representation theorem about or for positive linear operators on continuous compactly supported functions. So let's try to associate a positive linear operator to each of these lambda. So for every f continuous compactly supported that is pointwise positive, we set the following function operator phi of f is the supremum of all the value lambda of g, where g is any continuously compacted supported function that is pointwise in norm less than f. Okay. Now this is for positive functions. Now, if instead f is just a continuous complex supported function, so without f greater than or equal than 0, we write f as f plus minus f minus with each of these f plus and f minus compactly supported and positive. In other words, this is where the function has positive values, and this is where it's negative values. So it's easy to see that one can, these functions are still continuous and compactly supported. And when we write a function like this, we set phi of f to be phi of f plus minus phi of f minus. Okay, so this is again as a definition that extends to functions that are not necessarily positive. Okay, so let's claim first that this map phi is linear in f. So let f1 and f2 continuously compactly supported. So let's consider first the case where both of them are positive or non-negative. So here we have a soup, right? This is how it's defined. Okay. Now, for simplicity of the proof, let's assume that this soup is realized, so it's maximum. Okay. Otherwise, we have to redo the argument with an epsilon error. Okay. So, but now for the simplicity of the proof, so let's pretend for simplicity the proof that the supremum are realized. So what does it mean? It means that phi of fi is lambda of gi with norm of gi less or equal than fi. Then if we take g1 plus g2, then okay, the norm is less than g1 plus norm of g2, and each of them is less than the fi corresponding. So which means that this is a candidate to calculate phi of f1 plus f2. So we have that phi of f1 plus f2 is a supremum, so it's at least as big as lambda of g1 plus g2. Lambda is linear, this is lambda g1 plus lambda g2, and this was phi of f1 plus phi of f2. So for now, we proved one inequality for the linearity of phi. Okay, now let's prove the other direction. Now, assume exist h such that it realized phi of f1 plus f2 with norm of h bounded by f1 plus s2. And then what we do, we just split this h in two parts. So fi over f1 plus ff2 times h. When this sum is 0, let's just consider this function is 0. It's not important how to define it there. So we define this way the function gi, and then what we have that, first of all, okay, the norm of gi is less than these are f are positive. H is bounded by f1 plus f2, so this is less than 1, so we get that this is less than fi. So these are candidates for the calculation of lambda phi, phi of fi. And what happens when we sum g1 plus g2, this is h of f1 plus f2 plus h f2 f1 plus f2, which we sum up, and this is going to be equal to h. Then let's put together, hence phi of f1 plus f2 is a supremum, so it's at least as lambda of h, because h is a candidate. Now h, we saw that we can write it as g1 plus g2. Lambda is linear, so this is lambda g1 plus lambda of g2, and so this, and sorry, the first one, no, the first one, it was an inequality. The first one was an equality. No. Now, what we prove is that G1 is a candidate to calculate F1. In a second. Okay, so G1 is a candidate. So, but the supremum in general is going to be bigger. So this is F1 plus phi of F2. So we proved the other inequality for the linearity of phi. So what we concluded was that phi is linear. Okay, I proved on positive functions, but then one splits every function as the positive part and the negative part, and then you have the linearity of f. So phi is linear. Okay, so phi is linear, and also, of course, let's notice that phi is also positive. It's a positive operator. What I'm saying that if f is greater than 0, phi of f is greater or equal than 0. And why is that so? Because if I have g that is less than f, okay, because if I have that g is less than f, then also minus g is less than f. And therefore both g and minus g are candidate to calculate phi of f. So and lambda of g, it's equal to minus lambda of minus g. So one of these two numbers has to be positive. So when I take the supremum, I will get a positive number. Okay, so phi is a positive operator. Okay, now let's check this operator is not only linear and positive, but it's also continuous. Okay, so claim phi is continuous as a function on the compactly supported functions. Okay, so phi of f, we say by definition, is phi of the positive part of f minus phi of the negative part of f. Okay, let's just bound brutally as, so this now each of them is a positive number. So I will remove this, the absolute value, putting a plus. Okay. And now what you see, phi is linear, so we can, this is phi of f plus f minus. But what is this function here? This is exactly the absolute value of f. So this is equal to phi of the absolute value of f. Okay, and by definition, this is the supremum of lambda of g, such that g in norm is less than the norm of f. Because now I have the norm here. Okay, now phi lambda is continuous, so this quantity is less than the norm, the operator norm of phi times the operator norm of the norm of g. Now here we are taking g, in this case we are taking the sup norm, okay? And but okay, if g is less than f, then the sup norm of g is less than sup norm of f. So each of this quantity is less than this number here. So the sup has to be the same. So what we have, that this is less or equal than the sup operator norm of f of lambda times the sup norm of f. Okay, so we prove that the operator phi is bounded and therefore continuous. So what we proved is that phi is a positive linear continuous operator with norm bounded by the norm of lambda. Okay, so now that we have a positive linear operator, we can apply Ritz representation theorem. So by Ritz representation theorem, there exists nu, a positive measure on a space E, such that this operator phi is given as the integration respect to this measure nu. And this is for all function f compactly supported. Now let's this is the measure nu is not the measure we are looking for. So, because here we will only have a positive measure. Instead we are looking for a real valued measure. In fact, this is only true for compactly supported functions. Okay. Now, but nu is going to be the total variation of the measure mu we are looking for. Okay. So let's work a little bit on understanding nu as a positive measure. So first of all, okay, nu is a Borel measure on a boundedly compact metric space, and therefore it is regular. And therefore, since it's regular, there exists sequence of Kn larger and larger compact sets, compact, such that nu e is equal to the limit of this Kn, and the measure of this Kn, nu of Kn is finite. So in particular, so in other words, we have that nu is sigma finite. Nu is sigma finite. Okay. Now by Hudson lemma, Wilson lemma, we have that for all n, there exists a function, let's call it fn, continuous with compact support, such that, okay, the norm is less or equal than 1, and it's greater or equal than the characteristic of this kn. So it's 1 on kn, and then decreases to 0, having compact support. Okay. Now, so therefore, nu of e, that can be written as the limit of nu of kn, has a property that this nu of kn, so the c of nu of kn as the integral of the characteristic of kn in the nu. Okay. Now the characteristic is less than this function fn. Okay. Now fn are continuous functions with compact support. So on this for these functions, the integration with respect to nu is equal to the operator phi applied to fn, right? And phi is a continuous operator, so we can bound this this value with the norm of phi times the norm of fn, but the norm of each fn was less than 1, so this is less than 1, this is constant in n, so this is less or equal than the operator norm of lambda, which is finite number. So in particular, we prove that nu is a finite positive measure. Nu is a finite positive measure. It's good because to be the total variation of real valued measures are always finite measures. Okay. Now, okay, I'll write this, the fact that we're not only looking for nu, okay? No, that's a note for you. Nu is, or will be the total variation measure of the real valued measure mu we are looking for. Having lambda of nu equal to lambda. And we shall, and therefore we shall write the measure mu as a density function g times nu. Okay, so now we are going to look for g. Okay. Now, the fact that nu is finite, so implies that the integral of f in d nu for all f with compact support, so if the support is compact and it's continuous, so it's bounded, then this integral is necessarily finite. Because it's bounded by the sup norm of f times the measure nu of the support of f. Okay, so what we understand that, I'm just rephrasing that, the space of continuous compactly supported functions, this is a subset of the L1 functions with respect to the measure nu. Okay. Now remember this fact that the continuous compactly supported functions is dense in LP for p different than infinity. So this is a dense set. Okay. Now, moreover, for all f in the space of compactly supported functions, we have the operator lambda applied to f. So this is, we can write it as, we can bound it as lambda to f plus lambda of f minus. Okay. Now this is less by definition of the operator phi. We have the bound phi of, right? As we said before, this is phi of the norm of absolute value of f, and this is the integral of absolute value of f, and this is equal the norm, the L1 norm of f respect to the measure nu, right? So what does it mean? This means that this operator here, lambda f, can be seen as an operator on a dense set of L1, and on this subset it's continuous not only on this set with the sup norm, but also on this set with L1 norm. You have a function therefore defined on a dense set and therefore continuous, and therefore has a continuous extension. So what we deduce from this calculation is that lambda extends continuously to L1. So we can see lambda as an element of the dual of L1. But what is the dual of L1? The dual of L1 is represented by integration respect to functions in L infinity. Okay, so let's use this fact to represent lambda. So in other words, what we have that exists a function g in L infinity respect to the measure nu, such that the operator lambda applied to f is equal to the integration of f times g in the nu. And this is for all function in L1. Okay, we found our g. So now we define mu to be g times nu. Okay, now what we have is that this function mu now is real valued, and it's a Borel measure, and lambda of f, which is can be, because of this formula here, let's just call this function, this measure, mu. So it's the integration of f in the mu, right? And this is what we called the operator lambda mu applied to f. And this is for all f in C0 compactly supported. Notice that here there is a compactly supported. So now we know that this is equal to this on this subset. Okay, but this subset here is dense in C00, because it's C0. We saw that C00 is its closure, right? So then what we have, that since C0C is dense in C00, because we saw that this is the closure of this, we have that lambda is equal to lambda mu as elements in C00 star. And this completes the proof.